We've talked about physical and chemical changes and how chemical changes are usually associated with a chemical equation because our substance is actually changing in its nature. So when we write chemical equations, it's a shorthand way of describing a reaction. It gives us information about the reaction, such as the formulas of the reactants and the products. The reactants are on the left side of the equation, and the products are on the right side of the equation. And it gives us the states of the reactant, and the states are in parentheses to the right of each compound that we have or element, and the relative number of reactants and product molecules that are required, and these are represented by coefficients. So these here are the coefficients. We've talked about how you cannot change the subscript of a compound without changing the identity of the compound. And we've seen how carbon monoxide and carbon dioxide have completely different properties. So we can't change the subscripts, but we can add coefficients because we need to have an equal number of molecules on the left side to the right side. And that is part of having a balanced chemical equation in which the number of each atom on both sides of the equation is equal. And later in chapter 8, we can use these to determine the masses of reactants used and the products that can be made, which is very useful in the laboratory. Let us do a conceptual checkpoint just to make sure we understand what a chemical equation is and what all the numbers represent. In photosynthesis, plants make sugar, glucose, which has the formula C6H12O6, and they make this from carbon dioxide and water. The equation for the reaction is as follows. So in order for the reaction to be balanced, the coefficient X must be what? And we have these choices. Well, what this is trying to say is that we must have equal oxygen atoms on the left side to the right side. So let's count how many oxygens we have on the left side. Here we have 2 oxygens, but there's a coefficient of 6, so we have to carry this to the 2. So 6 times 2 is 12 oxygens. And don't forget we also have another oxygen here in water, and there's a coefficient of 6, so 6 times 1 is 6. So there's another 6 oxygens, giving us 18 total on the left side. Now that's got to be equal to the right side. On the right side, in the glucose molecule, we have 6 right here. There is no coefficient, so it's just 6 oxygens. And then we have oxygen gas released. So what is the X here? Okay, you could think, okay, I'll just subtract 6 from both sides and X is 12. But the problem is that there's a subscript of 2 here. So that means if X was 12, that means I have 24 oxygens. But that's not what we want, because 24 and 6, that would give us 30 oxygens. So that's not correct. So we have to divide the 12 by 2 to accommodate for the subscript. So X becomes 6. And so let's just make sure if we put a 6 here, 6 times 2 is 12, plus the 6 oxygens from here, that's 18. And so that equals to the left side. So our answer is going to be 6. Okay, let's see how we can balance chemical equations. And these are some of the rules in your book that break it down from step by step. First, we have to write the skeletal equation by writing the chemical formulas for the reactants and products. So we're going to do it for this problem right here. Write a balanced chemical equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide. So silicon dioxide, and this is solid, plus solid carbon. Notice I'm writing the name and I'm writing the state in the parentheses afterwards. And to produce, when it says to produce, that's when I put my arrow, because then my product will be on the other side. And then we produce silicon carbide plus carbon monoxide gas. Okay, so the next step is if an element occurs in only one compound on both sides of the equation, then we have to balance it first. And if there's more than one such element, we balance the metals before the nonmetals. So silicon occurs on in only one compound on both sides, and so does oxygen, right? So we need to actually start with the silicon first, because it's more metal-like than the oxygen. It's further left on the periodic table. So with silicon, it's already balanced. There's one silicon here and one silicon here. So we go on to oxygen. Well, there's two oxygens here, and there's only one oxygen here. So to make up for that, I don't change the subscript. Do not touch the subscript. You want to put a coefficient, okay? So we will put the coefficient of 2 here. So now 2 times 1 on the oxygen gives us 2 oxygens. So now we have 2 oxygens on the left and 2 oxygens on the right. Next, if an element occurs as a free element on either side of the chemical equation, then we balance it last by adjusting the coefficient of the free element. The free element is the easiest to change, so we leave that for last. All right, so now we have how many carbons on the right side? There's 1 and there's 2 here because we put the coefficient, so we have 3 carbons, right? Here we have only, on the left side, we only have 1. So let's adjust that by placing a coefficient of 3 right next to it. Now let us, the fourth step says if the equation contains coefficient fractions, then change those to whole numbers. But we don't have any fractions in this case, so we can skip that step and go to 5 and make sure the equation is balanced by summing the total. So let's sum the total. We have 1 silicon on the left and 1 silicon on the right. We have 2 oxygens on the left and 2 oxygens on the right. We have 3 carbons on the left and we have 3 carbons on the right. So it looks like we are all balanced. Okay, let's go ahead and do another example. Let's write the balanced chemical equation for the combustion of liquid octane with a formula C8H18. All other components of the reaction are in the gaseous state. And your book tells you exactly what the components are, but I want you to learn to recognize that a combustion reaction with a hydrocarbon, and this is hydrocarbon C8H18, right? This is found in gasoline. Let's see. Okay, and it's in the liquid state because gasoline is a liquid. And whenever we have a combustion reaction, it combines with oxygen gas, and it gives us carbon dioxide and water vapor. Okay, and as long as you have in a combustion reaction, as long as you have carbon, hydrogen, and oxygen, you will always end up with carbon dioxide and water as your products. This is because that's why we hear people talking about carbon dioxide emissions and how that's not good for the environment from combusting hydrocarbons. Hydrocarbons are found in fossil fuels, and they contain carbon and hydrogen, and we combust them with oxygen gas to give us heat, and that heat powers our cars, but we end up with this carbon dioxide and water, and carbon dioxide is a greenhouse gas, etc., etc. Okay, with that being said, let us balance the equation. We must look if an element occurs in only one compound on both sides of the equation. Then we balance it first. So we have carbon, it occurs on only one compound on both sides, here and here. And also hydrogen occurs in only one compound on both sides of the equation. So let us balance the carbon first. We have 8 carbons on the left, so let's put 8 carbons on the right. Now we want to balance the second one, which is our hydrogens. We have 18 hydrogens on the left, but we only have 2 on the right. So to make it 18, we multiply this whole thing by 9, right? So 9 times 2 is 18 hydrogens now. Okay, now here's the problem. The last thing that we have is we got to make sure we balance our free element, which is oxygen in this case. So it looks like we have on the right side 8 times 2, 16 oxygens here, and then 9 times 1 in water, 9 oxygens. So that gives us 25 oxygens. On the left side, we have 2 oxygens. So how do we balance that? We don't want to put fractions, right? Because 25 is an odd number. So what we usually do is say, okay, we have 25 on this side. No problem. I'm going to put 25 here. The only problem is if I do 25 times 2, that's 50 oxygens. So I'm going to half this. I'm going to put 25 over 2. Now look what happens. When I multiply this whole thing by 2 to get rid of the fraction, I carry the 2 to all coefficients. Because remember, in math, what we learned, you can, whatever you multiply one component of the equation by, as long as you multiply everything by that same number, you're mathematically all right. So now we're doing this just to get rid of the fraction. So this becomes 2C8H18. Now when I carry this through, this cancels out, and I have 25 oxygens. And here I have 16 carbon dioxides, and then I have 18 waters. Okay, so this was my 4th step. When I had a fraction, I had to get rid of it by multiplying the whole number by 2. Now, I just want to make sure that I have the correct numbers on both sides. So let's do, I have 16 carbons here on the left, and I have 16 carbons on the right. I have 36 hydrogens on the left here, and then I have 36 hydrogens on the right, and I have 50 oxygens on the left, and I have here 32 oxygens on this side, and I have 18 here, and that ends up being 50. So that's 50 oxygens, and I'm all balanced. All right, go ahead and give this a try. Write a balanced equation for the reaction between solid chromium-3 oxide and solid carbon to produce solid chromium and carbon dioxide gas. Okay, so I want to write the components of my equation, and the first thing is solid chromium-3 oxide. Now, chromium-3 is like this, and it combines with oxygen because it's an oxide. Oxygen is always -2. So remember, I just crisscross my numbers. My superscripts become the subscripts for the other element. And here this becomes a 3. And this is solid, okay? And this reacts with solid carbon to produce, so I put an arrow, solid chromium, and chromium solid is like so, plus carbon dioxide gas. Okay, now let's balance the equation. We look to see if we have an element that occurs in only one compound on both sides of the equation, and we see that we have chromium, but since chromium here is free on the right side, let's go ahead and balance oxygen, because oxygen occurs in only one compound on both sides of the equation, and the oxygens are tied up on both sides. Here the chromium is free, so that would be much easier to balance later if I need to adjust the coefficients. Okay, so I have 3 oxygens here on the left, and I have 2 oxygens here. So let us find a common factor, a multiple of that, and by doing the least common factor is 6, right? So here that means I would multiply this by 2. 2 times 3 is 6, and here I would do 3 times 2 is 6, okay? But now look, when I put the 2 here, yes, I balanced the oxygens, but now I have 2 times 4. I have 4 chromiums here, and I only have 1 chromium. So I'll adjust for that, no problem, because this is a free element. So I can put any coefficient that I want on there. So 4 on the right side by the chromium. Now lastly, I want to balance my free carbon. Here I have 3 carbons on this side, so very simply I'll put 3 here because it is a free element. So let me just double check. I don't have a fraction, so I can skip number 4, and I want to make sure that I have the left and the right side balanced. So I have 4 chromiums on the left and 4 chromiums on the right. I have 6 oxygens on the left, and I have 6 oxygens on the right, and I have 3 carbons on the left and 3 carbons on the right. So I am balanced.